Reduction of nitric oxide of ammonia over vanadium on pillared titanium phosphate. Our authors are L.J. Sarnicki, R.G. Anthony, B.D. Roberts, and A. Clearfield. And this work was performed at Texas A&M University. Our speaker is Larry Sarnicki. He is currently with Grace Chemicals, and he did his master's work at Texas A&M.
Thank you, Dr. Hopper. Can everyone hear me? Okay. I'd like to present our work we've done on the selective reduction of nitric oxide with ammonia on a vanadium catalyst with a pillar titanium phosphate support. The objective of our study, first of all, was to determine the activity of such a catalyst for the nitric oxide reduction reaction. Two reasons why we thought it might have be a good catalyst for this reaction is, first of all, it has a large surface area, typically larger than the titanium catalysts that are used. And we thought there might be an increased activity from the presence of titanium, which also occurs on vanadium supported on titanium catalysts. And second of all, to study the intrinsic kinetics of the reaction. A brief overview. The nitric oxide ammonia reaction reacts in the presence of oxygen to form nitrogen and water. Research has shown that when oxygen is present, typically greater than 1%, the reaction rate is greatly increased. Research has also shown that this mechanism appears to be a redox type of reaction, where the nitric oxide and ammonia react, leaving absorbed hydrogen probably on the catalyst surface, and the oxygen then reoxidizes the catalyst. Research has also shown that nitric oxide is typically not absorbed on the catalyst surface, or it may be weakly absorbed, whereas ammonia is strongly absorbed on the catalyst surface. A variety of different catalytic materials have been looked into for this reaction, and research so far has shown that vanadium catalysts tend to have the highest activity and are resistant to poisoning by sulfur dioxide. Alumina supports are typically poisoned by sulfur dioxide and ammonia through the formation of ammonium sulfate, whereas, as I mentioned before, titanium supports are resistant to this type of poisoning. In addition, titanium-supported vanadium catalysts also exhibit higher activity, even though they have lower surface areas than alumina supports. The material we were interested in was pillared titanium phosphate. In essence, it's just layers of pillared titanium phosphate separated by aluminum pillars, which are inserted use of aluminum kegonide. This was prepared by Brian Roberts, who's a member of Dr. Clearfield's research group. His preparation technique and some characterization has just recently been published in Inorganic Chemistry. Some of the physical properties of the catalysts that we used, measured by mercury, porosimetry, and nitrogen analysis, are shown in this table. The VTAP-12C catalyst is our catalyst, the vanadium pillar titanium phosphate, and the V-0601 is a commercial vanadium supported on gamma alumina catalyst manufactured by Harshaw. Both catalysts contained 10 weight percent vanadium. As you can see, our catalyst has appreciable surface area, typically greater than the titanium supports, which are nominally around 80 square meters per gram. It also has quite a significant amount of pore volume. The reactor system we used was a continuous flow reactor. Nitric oxide and ammonia were taken from cylinders, dilute mixtures in nitrogen, fed to a Pyrex glass reactor, which is heated in a fluidized sandbath. Nitric oxide was analyzed through the use of a chemiluminescence nitric oxide analyzer, and ammonia concentrations were measured by scrubbing the ammonia out of solution with boric acid, and then subsequent analysis with an ammonium ion selective pH meter. Before we began our reactions study, we decided to design the reactor based on these three constraints. Typically, the first equation is to minimize radial effects. The second equation to develop a plug flow profile. And the third equation was just inserted for ourselves to assume isobaric reaction conditions. These equations can be rewritten such that there's a relationship between catalyst particle diameter and reactor diameter. And knowing the physical properties of the reactant mixture and the catalyst and the gas space velocities that you're interested in, we determined the reaction condition. Reactor diameter, particle diameter conditions that would satisfy these three constraints. We chose a reactor diameter of 1.5 centimeters and then crushed instead the catalyst part, so we obtained particles that would satisfy the determined particle range. First of all, I'd like to show the effect of the support on the activity of the vanadium catalyst. As you can see, the pillar titanium phosphate catalyst had quite a lower activity. We've determined it's approximately about as fourth as active as the vanadium alumina supported catalyst. To go into the reaction study, we wanted to verify that indeed this reaction was occurring on the catalyst. And we decided to apply the first order nitric oxide zeroth order ammonia reaction rate equation. This has typically been used by a variety of other authors in the area of nitric oxide reduction. And for an integral flow reactor, this equation merely can be developed into this form. Comparing the ratio of ammonia reacted to nitric oxide reacted at various temperatures, we showed that indeed we had a one-to-one reaction stoichiometry between ammonia and nitric oxide. To determine if we had a first-order rate, we just merely plotted the last equation that I showed and indeed found a straight line fit through the intercept. To check to see if the ammonia indeed was a zeroth order effect on the reaction rate, we varied the ammonia nitric oxide feed ratio at low nitrogen oxide conversions. And over a wide variety of reactant ratios, you see that although ammonia might have a slight effect, it's virtually negligible. To determine activation energies and rate constant parameters, we used this modified form of the Arrhenius constant, where T naught was taken to be at 450 degrees C. This allowed for easier linear regression analysis of the data. Effectiveness factors were calculated using the White-Prater criteria for first-order reaction and using the random pore model proposed by Foucault and Smith for the which takes into account macro and micro pores of the catalyst. Arrhenius plot. For the two catalysts are shown in this graph right here. For the vanadium on pillar titanium phosphate catalyst, all the effectiveness factors were calculated to be greater than 0.98. So the intrinsic rate was essentially the same as the observed or global rate. For the vanadium alumina catalyst, the lowest effectiveness factor we observed was 0.8. So it made a slight difference between the global and the intrinsic kinetics. The rate constant and activation energies of the two catalysts are shown. And we've also compared our results to results published by Wong and Nobe in '87 for vanadium aluminum catalyst and vanadium titanium catalyst. And as you can note, the intrinsic activation energies of the Harshaw vanadium on aluminum catalyst were similar to that studied by the catalyst prepared by Wong and Nobe for similar vanadium on aluminum catalyst. And to check the fit of our rate equation, or how well it could predict the experimental data, show that it does have a very good fit, even though, like say in this point region right here, we're varying the ammonia concentration. So in conclusion, we've shown that ammonia and nitric oxide reaction, stoichiometry is 1:1. The reaction followed first order kinetics. We didn't observe any titanium promoter effect, which is as seen on titanium supported catalysts. In fact, we did see a lower activity. Reason for this we might think is due to the interaction of maybe the phosphate and the vanadium on the catalyst. Doing some research, we read an article by Hodnett and Delmont, where working with hydrocarbon oxidation catalysts, they've noticed that for vanadium phosphate catalysts, having an excess of phosphate tends to stabilize the reduced V4 oxidation state. And even though we haven't really followed this up with any analytical techniques, we think that there might be some kind of interaction occurring on such a catalyst. This concludes my talk. I'd like to answer any questions now.